Classical economic models operate on rigid assumptions, but applied to actual human social interactions, the math consistently breaks down. For decades, these models relied on the concept of Homo economicus, a theoretical agent designed to perfectly optimize financial payout. Under this framework, if an action yields a higher monetary reward, the agent always takes it. Biological organisms, however, do not calculate risk in a vacuum. Cognitive calculation and emotional states are integrated biological processes rather than competing forces. When an economic gamble involves another human being, the brain performs a specific set of anticipatory emotional computations regarding that person's intentions. By mapping the brain's dual motivational systems onto classic behavioral economics games, we can extract the exact neurobiology of trust, fairness, and betrayal. The brain generates behavior through two survival circuits. The approach system, centered in the ventromedial prefrontal cortex and ventral striatum, encodes appetitive value to orchestrate rewarding outcomes. Conversely, the avoidance system, driven by the anterior insula and amygdala, encodes aversive value to avoid threats. These same survival circuits parse the complexities of social environments, processing human interaction with the same urgency they apply to physical threats. These circuits alter the mathematics of economic decision-making. They assign a biological weight to social outcomes, creating incentives and penalties that traditional models ignore. To isolate the exact mathematical value of human intentionality, researchers compare two experimental setups. In the standard trust game, a human mediator decides your financial payout. In a risky dictator game, that same payout is determined by a random number generator. This excerpt from Bonnet and Zeckhauser's research outlines the minimum acceptance probability, or MAP. This is the exact threshold of guaranteed success an investor requires before they are willing to take a risk. When researchers run the numbers, the data reveals a sharp divergence. The required minimum acceptance probability is significantly higher in the trust game than in the risky dictator game, despite identical financial stakes. Betrayal aversion is the numerical gap between these two thresholds. It is a quantifiable form of social anxiety triggered by human-to-human risk. Humans demand a higher probability of success to risk intentional betrayal than they do to risk sheer mathematical chance. This psychological state of betrayal aversion corresponds to localized neural activity. Interactions with human mediators trigger specific neural alarms that random mechanisms do not. The anterior insula fires intensely during these human interactions, acting as an anticipatory emotional warning signal for potential betrayal. This text details findings from Kostfeld and colleagues on the effects of synthetic oxytocin. Administering the neuropeptide increased trust-taking in social games, while having no effect on non-social risk games. Oxytocin does not alter the brain's baseline risk tolerance. Instead, it suppresses the amygdala's reactivity to trust betrayal. Trust is a biological state that relies on dampening the brain's natural threat detection circuitry. We see this same biological override in the ultimatum game. One player proposes a split of a monetary sum. A perfectly rational responder should accept any offer greater than 0 to maximize their capital. Yet empirical data shows that extreme splits, like a 20-80 division, are frequently rejected. Social emotions like anger override the desire for financial gain. This excerpt highlights psychophysiological evidence gathered by Van Wout and colleagues. By measuring skin conductance, they found significant emotional arousal occurring specifically during interactions with human proposers making unfair offers. When responders are given alternative ways to express their contempt, such as sending a written message, the rate of costly financial punishment drops. Rejecting free money is a calculated transaction where the responder willingly pays a financial cost to purchase emotional relief. This interplay between biology and behavior is explained by the pain overlap theory, which identifies the common neural mechanisms shared by social and physical pain. Unreciprocated cooperation and unfairness trigger a literal emotional penalty in the avoidance system, a biological cost that exists alongside the loss of capital. Conversely, mutual cooperation generates a social reward bonus above and beyond financial gain, processed in the mesolimbic dopamine system. To accurately predict complex human social decision-making, the rigid framework of the perfectly rational economic actor must be retired. Economic models only align with reality when they integrate the calculable, biological impact of the human brain's anticipatory emotional systems.